iterative binary tree traversal algorithms. That's what we're talking about today. So, in the last lesson, we looked at using a recursion to implement a in-order, pre-order, and post-order traversal. Now, those traversals are great and all. They are depth first, but if we want to do a breadth first traversal, then we really need to use something else. And depth first traversals use what's called a stack, and breadth first use a queue. So we were able to implement a depth first searches fairly easily with recursion, because perhaps you've ever overly recurred and got an error called stack overflow. So a recursion is a stack. Every time you recall a method, every time we call, like, say, in order, which I'll just call IO, and I call IO, and then I call IO again, and I call IO again. Well, what's happening is all those things are going on a stack, okay? And so when one function method finally is completed, we go to the next element on the stack, which is the last function you called before that. So it should make sense that since I'm telling you now that depth first searches and depth first traversals use a stack, that we could implement it recursively. But if something uses a queue, recursion just isn't going to work for us. So we got to learn these things anyway. So I want to start with the pre-order traversal. The pre-order is the easiest depth first traversal to do with a stack. The others have some, particularly in order, has a subtlety to it that we just have to deal with. So you can get the idea here. And this is probably, I'm going to argue, the most important one for you to learn, because when we get to graphs in Unit 5, you'll be able to, if you know this traversal, you'll be able to traverse any graph depth first, no problem at all. So without further ado, let's go through it. Well, all right, so we're going to do let's see here. We're going to do, I'm going to scoot this over, actually. We're going to do a pre-order traversal. Pre-order. So pre-order is going to be called with the root. Okay, so if someone says pre-order, we're going to start at the root. Well, if the root is null, obviously, then we could just return. There's no traversal at all. I'm going to continue to use the word visit. I think in most of the assignments you're doing right now, visiting is actually adding the node to an array list. All right, so what we're going to do is we're going to create a stack of nodes. So this is going to be a stack of type node. So we're going to create a stack because depth first. A pre-order is a depth first, meaning that we're going to go down the tree as opposed to moving left and right like a typewriter or getting everything around L. The difference between depth first and breadth first makes more sense when we learn about graphs, but just picture a depth first traversal is going all the way down and getting A before you go get Q. So we're going to get A, which is down the tree, before we get everything that L is touching. And that requires a stack. You may not know why it requires a stack, but you will soon. Okay. So we're going to, first thing I want you to do is push the root on the stack. So I'm just going to call it L, okay? So we create a stack and push the root on it. We need to do that. Now, the other traversals have a slightly different setup. Each one's a little bit different. But for the pre-order, it's the simplest one. You create a stack, you push the root on it because that's where you're starting. And now we're going to enter a loop, okay? And our loop is while our stack is not empty. Okay? That should seem reasonable, right? And here's what I want you to do. I want you to pop a node from the stack, and we're going to call that current, okay? So we're going to pop, and since we just pushed the root on there, there should definitely be something there, right? So there we go. Pop that and call that current. Let's reference that current, okay? All right, so visit this node. So I'm going to we're probably going to have like, you either going to print it to the console, or if you're searching or looking for a certain thing. So we're just going to say visit list. So I would just add it to my visited list. So I'll put an L there, okay? Then what we want to do is, if the right child is not null, push it on the stack. You want to check that, right? Don't push null on the stack. It's just easier to check before you put it on there, okay? If you want to, you can allow pushing null, but then you got to check when you pop if it's null. But I check before I put it on there. So put right first, and then put the left node. Again, check that it's null. So why would we push to the stack the right node first before the left node? Well, that's because we are moving left, right? We saw that in each of the algorithms. This should go L, C, A, F, E, because we always move to the left in the pre-order, in order, post order. There is something called reverse order, which is pre-order but reversed. You could do reverse in order, which gives it to you backwards, but that would be moving in the other direction. And we know that stacks are LIFO, last in, first out. So if I want to move left before I move right, I need to put Q first in the stack, C next, so that I move left first. Okay? All right. Then that's it. That's the entire algorithm. Let's just go through and map it together, though. All right? So the stack is not empty. So I will pop from the stack. You want to call that current, right? I guess you could peek a few times if you wanted instead of keeping current, but I just pop and store in current. Then we're going to visit. And we're going to add the right child then the left child. Just check and make sure it's not null first. So I'm going to add F and A. And then I'm going to pop from the stack. Visit. And I'm going to add right then left, but those are both null, so I don't add them. Okay? Oh. When I popped earlier, I forgot to actually remove it. Let me go back to that. All right. So now you see we're ready to pop, and we are popping an X. An F, excuse me. Visit it. And add right, it's null, so don't add it. Add the left. So we'll add an E to our stack. Then we're going to pop. We're going to visit. And we're going to add the left and right, but there's nothing to add. So we pop. Pop again, that is. And we get Q. We're going to visit Q. We're going to add right then left. So we're going to add U and then M. Then we're going to pop. We're going to visit. Add right. Don't add left because it's null. And the process continues. Pop. We're going to add right. We're going to visit. We're going to push right, push left. And then what's going to happen is we're going to pop the in. Nothing's going to add. We're going to pop the P. Nothing's going to add. We already popped the O. So then, once again, I kept forgetting to remove these things when I popped them. So if that finally brings us back to the U, we'll visit that. So U goes there, and we will add a W. Then we'll get the W. Mark that as current, and we'll visit it. There is nothing to the left or right, so we don't add anything to our stack. Again, when I popped it, I keep copying instead of cutting. When we pop it, the stack is now empty. We exit the while loop, and you'll notice that we have visited all of the nodes. All right, so now would be a time you could complete part A of the first exercise. All right, now it is time for us to do the in order. In order is a little bit different. It's got a little twist to it. So once again, we're going to create a stack. Of course, if the root node is null, just return. There's nothing to. I got a visited array list here. There's nothing to visit if the root node is null. All right, we're going to go ahead and create a reference to the root node right now. So that's a difference. Earlier we had current node created inside the while loop. But we're going to start with current equaling the root first. So that's going to be an L for me. Then we're going to enter the while loop like this. We're not going to, so last time we didn't actually reference current first. We just pushed it on the stack. We're not going to do that right now. We're going to make our condition of our while loop. We're going to say while the stack is not empty. Or current is not null. So we have two conditions. So it is okay for our stack to be empty this time as long as current is not null. All right, and then this is what we're going to do inside our while loop. What we're going to do is we're going to make another loop that says while current is not null. And while that's happening, we're going to be pushing the current to the stack and setting current to current.left. So we'll push current and push, so let me just write push current. And I don't need to write this in code. Let me just write it in plain language. So we're gonna push current and move left, okay? Or what I like to call dive left, okay? So we're going to keep doing this while current's not null. So this will make sense as we go through it. So we set current to L, and we're going to be in this while loop while the stack is not empty and the current's not null. But while we're in that while loop, we're going to be having a little while loop here. So current is L, and while current is not null, I want you to push it to the stack and dive left. Push it to the stack and dive left. So I went here and here. And I do that by using current equals current.left. And then at this point, we're going to dive left again. But that's null. So that's going to exit my loop. So what's the purpose of this inner while loop? The purpose of that inner while loop is to dive as far left as I can at any time. Because it's in order. We need to start with the bottom left-hand corner. So that's why we have to do that. Okay? Then, after you've done with that while loop, then we're going to pop, finally we're going to pop something, all right? So then we're going to pop a node, and I'm going to set it to current. So remember, at that point, current, mine says current equals L, but at that point, actually, current would be null. That's what made it break that while loop. Now current is A, and we're going to visit, we're finally going to visit. And remember, with in order, you go left, you visit, then you go right. So now I have to dive right. No, this is outside of it. It's inside this one, though. So I visit A, and then I dive right. Well, right is null. So this is null again. But remember, our while loop, that's the end of the algorithm, right? The while loop is while the stack is not empty or current is not null. Well, the stack is not, current is null, but the stack is not empty. So we are going to enter the while loop, okay? And then here's this inner while loop. It says while current does not equal null. Well, current is null. So then we're simply going to pop. So we skipped this while loop entirely because current was null. So we then pop. We're going to pop that. We're going to visit it. And then remember, you go left, you visit, then you go right. So then we dive to the right. So I was at C, now I'm diving to the right over here. Okay? And I'm going to F. And after I dive right, now we go back up to the loop because we dove right. It says while the stack is not empty or current is not null. Well, neither the stack is neither empty nor is current null. We're going to enter this loop and it says while current is not equal null, we're going to push current. So we're going to push current here. And then we're going to dive left. So I'm going to dive left. I'm going to dive left. This while loop means keep diving left until you reach null. So you get this sense that we just keep going down left as far as we can. Then we backtrack one, go right. If right is null, we'll backtrack again. Go right. Dive left. Every time you go right, you dive left as much as you can. So I dove left. Finally will be null. Finally, current will become null as I go to the left child of V. So I have to pop. What do I? When I'm diving left, by the way, I'm pushing current as I go. So we were F. While current is not equal null, we push current F. Then we dove left to E. Push E. Then we dove left to null. Then we pop. So we'll pop that. And we'll dive right. And when we dive right, that's null. So we go back to the top. The stack's not empty. Current is null, though. And so we won't enter this while loop. We'll just simply pop. That's going to be current. All right. And then we're supposed to dive right here. So when I popped, okay, sorry, I popped F. I didn't visit it though, did I? You've got to pop and visit. We've been doing that, but pop and visit. There we go. Now I dive right. That's null. So I come back, and that's null. So we'll continue. The stack's not empty. This is null, so finally we'll pop. We'll pop an L. We'll set it to current. We'll visit it. So after you pop from the stack, set it to current, then visit. All right, we're going to get to this situation. This happens every time when you're at the... Every time you get back to this root, what's going to happen is this stack's going to be empty. But our current won't be null. So we will end the while loop. No, I'm sorry. After we pop, we have to dive right. So actually, when we dive right, current will become Q. Q. Then our stack is empty, but we have Q for current, so we'll dive left, and as we dive left, we put current on the stack, dive left, M, put M on the stack, dive left, null, so we pop, and we visit M. So now the way that goes is after we visit M, okay, that's null. So we come back, we visit M, and we dive right. Because our current node is not null, we dive left. We dive left, it's null, so we come back, we visit. We go back to the right. That's null. So we go here, we pop, we visit, we dive right. So just keep that in mind. Pop, visit, right. So the idea is you go left as far as you can until you can't go left anymore. You pop a node off to go back a step because you went too far. Visit, dive right. So that, in a sense, is in order traversal. All right, next we have iterative post-order traversal. So the hard one is in order. Post order is not that bad. It does use a little bit of a trick. So what we're going to do is basically post order is reversing your pre-order. So it's not too bad. We're going to make a stack of nodes again, but we're also going to make a queue. Oh no, not a queue. I'm sorry. We're going to make another stack. So this is a stack that I call. Just stack. And then this other thing I'm going to call, it's another stack, but we're going to call it toVisit. So we have two stacks. One stack is handling our traversal, and the other stack is the nodes that we're going to visit. All right. So we create an empty stack called stack, create an empty stack of nodes called toVisit. And we're going to push the root on the stack. So this sounds exactly like the beginning of the in order. Then while the stack is not empty, we're going to pop a node from the stack and call it current. So again, we're defining current inside our while loop. This is the while not empty, right? So I pop a node. Set it to current. Then what I'm going to do is I'm going to push current onto the toVisit stack. All right? And then last time when we did pre-order, we pushed right then left. Well, this time we're going to push left and right. So I'm going to push C and then Q. All right? And then that's it. That's really the algorithm. So you're going to pop a node from the stack. You're going to add that node to toVisit. Then you're going to add to the stack left then right. So left then right would be backwards, but we're doing another stack over here, which will reverse it. So here we go. Let's do it a few times. We don't need to go through the whole thing. Let's pop a node. We'll pop Q. That becomes current. And I add it to my toVisit. And then I add left and right. So M, then U. All right. Then I pop. Add it to toVisit. Notice I'm not visiting right now. I'm adding it to my toVisit. I add left is null, so then I don't add it, and I add right, because I'm checking before I add. Okay. W. All right, and we pop. That goes there. I add it to my toVisit. Nothing to add to the list. So I pop again. I add it to toVisit. And I add left and right. Left, nothing on the left, but I add to the right. I pop. Add it to toVisit. Add the left and right. Left, then right this time. NP. I pop. Add it to toVisit. Add the left and right. There's nothing to add in left or right. Then I pop again. There's nothing to add. But I add it to my toVisit. Okay? Then we pop again and we get, finally, guess what? We finally got our C. So with C, earlier I pushed this on the stack and popped it. I'm sorry, I should not have this L anymore. Sometimes I have trouble doing these algorithms on paper. All right, so current is C. We're going to push the left and right. So push A, push F, add C to the toVisit. Then we're going to pop the F. We're going to add it to our toVisit. We're going to add its left and right. So we're going to add an E. Then we're going to, we're going to add an E here. Then we're going to pop, add its left and right, and put it in our toVisit stack, which is getting kind of long. Then we're going to pop, and we're going to add its left and right to the stack, and we'll add it to the toVisit. This stack is now empty. We exit the while loop, and here's how you actually visit. You take your toVisit stack, and you just start popping. A, E, F, C, N, P, O, M, W, U, Q, L. So remember, it should be touching on the right-hand side. So A, E, F, C, N, P, O, M, W, U, Q, L. And that is all. All right, we have one last algorithm to learn on traversals with iterative, and that is the one that has to be done iteratively. As far as I know, if you know a recursive way, I mean, I wouldn't be surprised if there is one, but I don't know it. So this is level order. This is our first breadth first search. And we're going to use a lot of breadth first searches in this class, or BFS as they call it. Well, this is a BFT. It's a breadth first traversal. But if this was not like a binary search tree, we would be searching. All right, so here it is. Depth first uses a stack. Breadth first uses a queue. Because you're searching everything around you as close as you can first. So you simply create an empty queue of nodes, all right? And we're going to offer the root to our queue. So I'll put my root right here, L. Then this is really just like the pre-order. So it's just while the queue is not empty, okay? While the queue is not empty is our loop. And then what we're going to do in the loop is we're simply going to pull the queue. So that's my current. And then we just offer to the left and right to the queue if they're not null. So I'll offer a C, I'll offer a Q. And I'll go ahead and visit, right? So you pull and you offer and you visit. The order doesn't matter there, just as long as you offer left and right, for left then right. So I'm going to visit L. Then I'm going to pull. I pull a actually, maybe the order does matter. Oh, no, we're pulling because we pull from the front. Okay. All right, sorry. A little bit of a lapse of judgment there. So pull, it's a Q. Get from the front, you get a C. So we're going to put a C here on our visit, and then we're going to offer to the Q left, then right. Then we're going to pull. This is getting fun now. There goes the Q. I'm going to move these up. And after the Q, what do we add? We add left. We offer right. We visit. and we pull. I get an A. So we offer left and right. There's nothing there. We visit it. So we pull. I get an F. We offer left and right to the Q. I visit. We pull. I offer left and right. We visit. We pull. I offer left and right. We visit. Oh, darn it. We visit. The polling puts it there. Our offering puts it there. All right, now we are ready to poll the E. We offer left and right, which gives me nothing, and we visit. We poll. We offer left and right. And we visit. We poll. We offer left and right, and we visit. We pull, offer left and right, and we pull. The Q is empty, and we're done. L C Q A F M U E O W N P. Level order, breadth first, searching all of the neighbors first. And so that's it. So now you should be able to take our tree viewer application. You should be able to implement level order, and you should be able to redo pre-order, in order, and post order so that they call an iterative version, and check them out. All right, good luck.